Morning. And I thought, although we talked about a few slides here last time already, it wasn't quite optimal the way that I described it. But given credit to the importance that I think that signal detection theory plays, I want to repeat that and make it clearer to why we're talking about that in that detail. Okay? I think this is at the heart of everything that we do psychologically, to understand how we get from a measure of physics to a measure of psychology. So, or as we already said, what's the motivation is for our case, what is a threshold? And thresholds, there is another seat over there. Thresholds are at the heart of everything that we measure, certainly with pure tone audiometry is the best example. But it's also the most widely used psychophysical method in general if we measure any other kind of just noticeable differences, or well, not so much for speech tests, but clever experiments do that. Why do we try to measure thresholds? Because thresholds are easily repeatable and should be fairly stable. Morning. There's another one more. Oh, two more seats over there. Right. But we concentrate here on the perception of a sound, of a pure tone, a noise. And the noise, in a second, I will add artificially, but in the real world, the noise is obviously external and internal. And the problems, as we discussed, are the people are different, and the decision criteria that I'll explain today in more detail. If you printed out that lecture slides from last week, this is a bit of a repeat. I'll have swapped around 2 or 3 lecture slides, so please stay with me, and I've added one new lecture slide that you'll discover here as well. Right, the experiment we already did last week. We do it again just for your listening pleasures. Tell me how many beeps you hear. Let's start that again. The first one I think is it's just a beep, and then just the noise without a beep. Let's see. That's just the beep. And that's just the noise. Both. Okay, different from last week. How many heard 4? Possibly 5. How many heard 5? 6? Most of you 7. Really? Oh, death. Scares me. Right. That is what we call the yes-no paradigm. You hear and you say yes, you hear it, or no. And I take it on your trust that you hear it. It's like PTA, you press a button every time you hear it. Okay? So the disadvantage here is clearly you can cheat. Well, if you want to cheat. The advantage is it's the fastest possible method, because we just count and be over with the whole PTA in 3 minutes. That would be nice. The problem with that is subjects are different from each other, and to improve that, the problem is that there is no correct answer for a threshold, because the correct answer for your subjective threshold depends on a number of factors, mostly on yourself. What you in your head define as a threshold. That's what's called the criterion. And furthermore, yes is always the correct answer in case you want to impress the tester or you want to cheat, which you might, well, you don't know. You want to take that out, that argument. Now, we have explained the psychometric function. I changed it a little bit now just to say how many people heard these numbers of steps. So, for example, few people heard 7, actually, well, a bit more. More people heard 6. Half of you heard 5, few only heard 4, and very few heard 3. That's kind of psychometric function. If we repeat that experiment 100 times, you can do that with the population, assuming that you all have the same hearing. You can do it with yourself 100 times. Ideally, as I explained, you want to have a function like that. You always hear 5, you never hear 4, you never hear 6, you always hear 4. That's not the case. Therefore, we need to understand this psychometric function where we then have a maximum threshold or a maximum slope, which is around a certain point, and we call this usually the threshold 50%. But we have other thresholds that we'll define later on. That can be 75, 79, 83, or whatever percentage we want. And then the experiment becomes harder, but also better. Right. What are the sources of variability, or the sources of noise? The problem within in all of these experiments, and there are three. One is external noise. Can't do anything about that. That's our external noise, or that's the lorry that is driving past the house just when you listen to one of these tones. Okay? We're trying to control that as much as possible by putting people into a soundproof booth, but that's all that we can do. Well, actually, to be fair, we have that under control because we could put people into a soundproof booth. What we cannot do anything really about is the internal noise in the subject. That is your heartbeat, your tinnitus, your concentration. You're feined in and out, you're just not concentrating hard enough, forget what you do, you fall asleep. Happens. The third one is the one that we can control, and that's the internal response of yourself towards the sound. That's what I was trying to explain in many words. You have in your heads the impression, yeah, there might just be a sound. So I press the button because I'm daring. Or, no, I want to be really sure that there is a sound, and I don't press it for a while until I'm really, really sure. And that's what we're going to investigate now, this criteria. And to do that, we develop a better experiment, namely a criterion-free experiment. And that's the one that is always used in psychophysics. Yeah, not always. This is usually. Namely, I play two intervals, interval A and interval B. And only one of them contains the sound. Over to you. Which one? Well, I didn't hear it, but you're all good listeners. No? Okay, do it again. Make it louder. Oops. No? Okay. It's below threshold then apparently. But the point is you have to choose. Give me one of two. Okay. And you might be right. I don't actually know what the answer is. We should check that. But the point is we can increase or decrease the SNR, and you might be right even if you don't know it. You wouldn't believe that, but that is very often the case because your ear might be better than your conscious perception of that. That happens all the time. But the point is, I don't want to know what you consciously say yes, or what you actually think about it. I want to know what your auditory system thinks about it. And that's why we do this here as an improvement to the simple yes-no. So I play you two sounds, two intervals, sound and noise, just noise, or the other way around. That's called two alternative forced choice, two alternatives, and I force you to give an answer. You cannot say I don't know. I force you to give an answer. 2 AFC. The advantage is you cannot apply a criterion to that. Independent of what if you're daring or not, you either hear it or you don't, and you will press the button, or not. And that's the advantage of these these forced choice experiments. I force you to do a decision, and I know what's right, but you don't, and so I can criterion-free check on you, so you can't cheat. The disadvantage is I have to play twice as many sounds, at least. Actually, there are a few more even, but it takes longer. And if you just guess all the time, you get 50% of them correct. So we cannot use 50% here as a criterion. We'll develop that a little bit further in a second, where I tell you how you actually increase or decrease the sound, the SNR. But first, let's understand again my decision axis and our decision criteria to see what we're talking about. Right. This is a probability density function, and I now assume, and now I jump 2 slides ahead, but this is the more logical order. I assume, I show you both of these. I have 2 of my intervals, namely the interval with noise and no signal, and the interval with signal and noise. And this axis is in your head. That's what's called decision axis. That could be the number of times the decision brain area in your prefrontal cortex, if it exists, fires spikes, if there is either only the noise or noise and signal. It must be in your head somewhere. It's a little homunculus pressing the button. But it must be somewhere in your head. It's not something objective, it's very subjective. And this guy either knows that there is a signal or knows there is no signal. But this is not a clear yes-no decision. It's always distributed. So either, and you can call that either with just an energy, but I don't like the energy. It's more like this number of spikes that your decider calls it, or I just call it a general internal response. The point is, there's a probability for this criterion or for this interval only with the noise, or the signal and the noise, and they are broad and they are different from each other. Okay, so what do we do with that? We first, this is what I did last time, have these possible outcomes. Now either I'm the experimenter and I know there is a signal and noise, or there is no signal in there, and this is you, the subject doing the experiment. If I present to you the intervals with a stimulus, you say yes, we call it a hit. If there isn't one and you say no, that's a correct rejection. They're green because they're good. The other two are the errors, false alarm and the misses. And this is the one slide that I included for you to never forget again what a false alarm and a correct rejection is. And that happens. And we don't want these, obviously. We want to minimize these errors. But these errors are unavoidable. So that's the problem. Errors happen. And but obviously these things, because they happen, we need to quantify them. And let's quantify them and make the pregnancy test our PTA, because it's exactly the same thing. When you do a test, you say yes, you hear it, yes, you're pregnant. No, you don't hear it, no, you're not pregnant. Same thing, yeah? Same logic is applied, and in fact, this is where both of these areas are totally applied. Okay, so what we define is the difference between these two decisions, namely the noise and the signal and noise. There's a difference between these, and they both have a variance, which is the width of them. And we define that the difference divided by the variability is what's called the d prime value. And so the d prime in not so many words is a ratio, is a measure for how much do they vary, the interval and the interval plus noise, divided by how much internal noise there is. Okay, let's look at that. So the d prime is the difference, the distance between the two measures, and the variance, and it's a criterion-free estimator, because this is now measurable, or we're going to measure it depending on the response of the subject. Okay, now let's do an experiment, and we'll explain a couple of different kinds of observers. The 18-year-old excited person and the 75-year-old resistant person, or whatever you call it. And the ideal observer sits here in the middle, because what the observer can do, now, it cannot do anything about these distributions. They are in your head. They make these two observers, or this one observer looks at these distributions and decides, I press the button, or I don't press the button. And in the ideal world, you would put your decision, you can choose in your head where you put this decision anywhere on this axis. If you put it in the middle, that looks kind of optimal. Why? Because the red is to the left and the green is to the right. Why that is exactly optimal, I'll tell you when we move that around. Now here, we have our daring observer, which, these are the green ones. He always wants to press the button when he even barely hears the sound, okay? So he will capture all of the noise, of the responses, of the signals and noises. He will have many hits, that's good. But he will also produce lots of false alarms. And we'll see in a second how we can read that from that. I'll show you the other observer, which is the cautious observer. He wants to press the button only when he's very sure. In other words, he wants to maximize the correct rejections. He never presses the button when he isn't really, really sure, but he only gets very, very few hits here as well. Sorry, he gets very few misses. So he also not good. Okay, let's see what these, that's our cautious observer. This area here, under the green curve, is the probability that he actually gets a hit. And the probability here to the left is the probability that he gets a miss. So obviously the probability to get a hit is bigger than the probability that he gets a miss. And the other two, the probability that he gets a correct rejection is very, very high, but the probability to get a false alarm is very, very, very low. So it's a cautious observer, never gets or rarely gets a false alarm, almost always gets correct rejection, gets a fair number of misses, and gets a high number of hits. So these are how these four, there are only these four areas underneath. And if I want to optimize my two, I go back, I want to put my ideal observer in the middle, because then the probability of the signal of the hits is maximal and to the correct rejection. Okay, that's a little bit confusing. I know that, and you have to go over that obviously at home. But there is one way to plot that, and that's what these called these ROC curves, receiver operating characteristics, which hopefully actually makes it clearer. Namely, we can measure the false alarm versus the hits. Let's say you do this experiment 1,000 times, yeah, and we get 50 false alarms, 70 misses, and you get 420 correct rejections, and I don't know what the number is, 620 hits. Yeah, all of them add together to 1,000, but you get these two crucial numbers, namely the false alarm and the hits, and you plot them against each other. And what you get then is a receiver operating, which indicates the criterion-free point of where you are in this criterion. And I think I should put a curve on there, because I haven't really done that. That's what I took out. So we've got these, they go both from 0 to 1, okay? Where do you want to be in an ideal world? You want to have high hit rate, you don't want to have a false alarm, so you want to be up here. Yeah? So if you do lots and lots of experiments, you get a curve like that. That would be perfect. But we are usually not perfect. What's the most imperfect? The person is always guessing. That's this line. If they're always guessing, they produce exactly the same number of hits as false alarms. Now what is guessing indicating in, I go back to the in the D prime, you might wonder. Well, D prime indicates that the D prime is 0. There is no difference between that. And this line in the receiver operating characteristics indicates exactly D prime equals 0. There's no difference, the person has to guess. You cannot actually, well, you could get theoretically worse than guessing, but then something weird is going on. You're usually always above this line. For example, this observer A here, what would produce a curve, something like that. You do that experiment very often, you get this curve, which is above that line. And these lines are always indication with something around, if it looks like that, something D prime equals 1. Which means the internal variability is about as much as the difference between the two. And that's good. That's what we usually call threshold. That's actually a very good definition of the threshold, because that compares between people, between experiments, between anything. It just tells you that person can differentiate these two signals because they produce that much hits and those many false alarms. Okay. That person here just guesses, and that person here is even better. So that would produce a curve like that, and it's even higher on the hit rate with less false alarms. If you're an ideal observer, you would actually sit exactly on here, because this is the maximum. This is always the maximum. You go away from this diagonal, you're not optimal anymore. You change your criterion to either to, what is it, to daring, which means you produce more false alarms, but also more hits obviously, or you're too cautious, less false alarms, but also less hits. That's the logic. Now that's a very quick run through in 20 minutes, but that's what you have to internalize somehow, these two things. And if you do that, you also understand what sensitivity and specificity is, because you might wonder, this is actually coming from medicine, where we're trying to find medicine is useful for something or not. We want to actually, they don't talk about hits and misses so much. Think about pregnancy tests. They think about sensitivity and specificity. Sensitivity means, do you detect, or what is the probability that you detect an issue or a condition, like it's pregnant, which is by definition the number of hits divided by the number of hits plus the false alarms. And similarity, the specificity, which is the probability that you detect that something is there, is the correct rejections divided by the correct rejections plus misses. So that's all together what we need to understand. So we start with a fuzzy system, which is our subject, and they only have two answers usually, yes or no. But me as an experimenter, I need to make sure that I present the right stimuli to them so that I get an optimal result from them. And I want to let them work at a point where they're optimal, which is decision-free. And what do I do to make them decision-free? Well, I don't ask them, press the button when you hear the sound, but I ask them, press the button in which interval you hear the sound, and then they cannot apply their criterion. Okay? So you do, that's the logic that we're doing with better experiments. If I ask a person just to press a button when if they hear a sound, they apply a criteria. They apply their internal criterion of being either cautious or daring. So they will, without your understanding, without your knowledge, shift their internal representation that you have no control over to the left or to the right. They can either be daring, so they want to have all the hits, but they also get lots of false alarms, or they want to be cautious, so they want to have lots of correct rejections, but you get very, very few hits. Yeah? So what we want to do is develop an experiment, and that's actually your task for till Friday. Develop an experiment that lets us measure pure tone thresholds, decision-free, criterion-free. Sorry, not decision. We always have decision criterion-free, so that the subjects cannot cheat, and independent of which kind of mindset they bring in, they will always produce the same result. Okay. Now that we have that wonderful method, two alternative false choice, we can even make it slightly better. And if you read papers about psychophysics, you will encounter that often, because we can improve it by making more choices, but still force the subject to have a choice. Then you get what we already had, is the two alternative, 2 AFC. And if they're guessing, then obviously they get 50% correct. But we could do 3 alternative false choice, which is I give you 3 sh, 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 and in one of them is the sound. And you have to tell me which one, A, B, or C, is the sound. Why do I want to do that? Because it turns out that it's faster and more reliable. Because if you just guess, you only get 33% correct, because one of them has to have it, obviously. You can do 4 alternative false choice or whatever, but the actual, if you read literature in terms of psychophysics, the 3 alternative false choice is by far the most widely used one. Okay, if we have that, we need to talk about one more thing. Namely, the adaptive. What do we do in methods in practical methods? You still want to know a threshold. You want to know where a subject hears something. So we need to define a threshold. We get to the definition later on, what actually we define as a threshold. But you need to start with something that people hear, as we do in PTA. That is a very simple threshold method. Okay? You start with something that a person hears, you make it quieter. If they still hear it, you make it yet quieter. If they not hear it, you make it louder. Yeah? That's what's called a staircase method. Because why? Because let's say you start very, very high. The next step go down and down and down. They don't hear it, you go up, and you go down and down. Because they don't hear it, no, they hear it, hear it, hear it, hear it, don't hear it, hear it, and so on. You know what I mean? Yeah? And that looks a little bit like a staircase. Okay, let's objectify. Let's make that a little bit more objective and define how that works. What is usually used in psychophysics is what's called a 2 down, 1 up threshold. Yeah, what I just drew on the board is a 1 up, 1 down. They hear it, you go down. They don't hear it, you go up. Yeah? So every time they hear it, you go down. Every time they don't hear it, they go up. 1 up, 1 down. Let's make that slightly more expensive by inventing a 2 down, 1 up. Now what does that mean? But at the beginning we start with something that they hear very well. And this is the same as a 1 up, 1 down. They hear it, they hear it, they hear it, and they don't hear it. But the first time when they don't get it, you go up, and from now on they have to be twice correct to hear it. Why? Because there is otherwise too much guessing involved. If you just do it every time, well, if you just do it once, 1 up, 1 down, they have a 50% chance of getting it right, which means they will fluctuate quite widely just by guessing. That's kind of a random walk. Don't know if you know that, but if you do that, if you actually just guess, you put a monkey doing the PTA and they just guess yes or no every time, you might get very, very low thresholds. Although the person is just guessing. Why just for randomness? So you have to completely work with the collaboration of the patient here. If you don't want to work with the collaboration, you don't trust them, or you want to know it more objectively, you invented a method like that. Why? Because if you're guessing, what happens if you're just guessing in this method? Where you go? Say again? You would give the answer for one. Yes, you just, let's assume your subject is just guessing every time. Nothing to do with hearing, just guessing. But what would this curve do? Remember, you need twice to go down, one wrong to go up, twice correct to go down. Yes. Yes, please. I can tell you we have everyone plus 2, 32.
Plus 2?
Yeah.
Lovely, thanks.
Which means we need a bigger room. Yeah, anyone? So, it's going up and up and up and up. It's going up by default, yeah? Because you need twice to go down. Well, you get, let's say you get 10 responses that are random, 5 of which will on average be up, will be up, but no, 5 will be yes, 5 will be no on average. Every time you get a no, you go up, but only twice in the right order you say yes, you go down. So on average you will go up and up and up and up.
When you call that, you play that same.
Saying the same sound, yes. Difference here, just you could say, we always say different because it's decibel, but it could just be level here. That's 60 dB, 50 dB, 40 dB, 30 dB. 30 dB it didn't hear, so you go up 40 dB, and you play it again 40 dB. And only if they heard 40 dB twice, you go down again. Yeah. So this is a really genius way to force the subjects to be true, if you like. Because if they fall asleep and they start guessing, you can just go up and up and up and up until they get 120 decibel.
Going down by the same value and up by the same value, or
Yes, usually. There are a number of parameters in here that can be optimized, but in the standard, in the easiest form, yes, you do go down by the same token. Usually there's already one trick in here, so at the beginning I start with something very loud so that they know what the sound is, and I don't actually do the two up, I actually do one up, one down. But you can also say, okay, you go up higher, then you go down lower. There's a number of tricks, but the concept is always the same. If they start guessing, stimulus goes up. Right. So that's efficient, I say here. Why is that efficient? Well, where is it difficult for the subject? Let's say this is steps here. I hope I said that. This is easy. Yeah, because I start very, very loud. This is easy. This is easy. This seems to be difficult. I needed to guess. But the point is, what is my threshold? Where in this you would say now is the threshold? Don't really know. We need to define it. The definition of the threshold is here, which is, I didn't actually say it, but the standard definition of the threshold is we take the reversals. So that's a reversal, that's a reversal, that's a reversal, and that's a reversal. You see what I mean by reversals? And you get top reversals and you get bottom reversals. Reversals is always you change your direction. Here you change it from down to up, and here you change it from down to up. And with the green ones I change it from up to down, and the same. Yeah? The definition of a threshold is all of my ups divided by all of my downs. Or just the average of the last, usually it's 2 or 3 pairs of reversals. So the threshold is just defined as you're going. Well, you're going in a zigzag line. Yeah, we can continue that. Sometimes you do continue that, it goes something like that. Because here you always hear it, here you don't hear it, so you go zigzag. And then you say, okay, I'll take the last, I don't know, 2, 3 reversals, and I just average them, and that's my threshold. And I kid you not, that is what is done. It's fairly straightforward. It's actually very simple to do.
did you say take all of your ups divided by all of your downs?
Not all of them. You usually discard the ones at the beginning because you expect the person to get to listen into the sound. So what we usually do in experiments, or have done, is 10 reversals, and you discard the first 4, you take the last 6 and take the average. Yeah. Now that is a good definition of the threshold, because I can write it down first of all. It's completely criterion free. It's reproducible. And what I mean here, if I do an experiment, I don't want to waste time to play stimuli that I know the answer to. Very loud sounds, so that they definitely hear them, or very quiet sounds that they definitely don't hear. That's why I want to start with something that I know that they hear, but that very quickly go into the area where they don't hear it. I want to operate, that's right again, so this is my zigzag, but this is exactly where the threshold is. So all of my stimuli are pretty much at threshold. So I don't waste any time of playing a sound that is very loud, which they always hear, or a sound that they will not hear. Why bother? I know that the threshold is somewhere around here, and I just want to specify it more. That's why I go do something like that, where they spend all of their time around the interesting part. Yeah, shifts observers to be at the optimum decision part. Because of the design of the experiment, they will be automatically ideal observers, because they can only say yes or no. They have to guess. If they don't know it, they have to guess. If they do know it, they will say, well, A or B. They don't say yes or no, they say A or B. That's the point. Good. So that's a good experiment. And equilibrium level is the last point that we need to see here. That's the point where we're guessing, where we have a 50-50% chance of getting it right. That's, well, where's the point where I have a 50-50% chance of getting it right? You see there in the middle. That's what I call the threshold. That is the threshold. 50%. And with the yes-no, with one AFC, I have a threshold of 50%, and with the two AFC, two alternative forced choice, I have a 70% chance of getting it right. Why? Because I need to press yes 2 times for going down, but only once for going up. And that on average gives you a 70% correct value. So the threshold in fact isn't 50%, where I hear it 50% of the times, but because of this modification with 2-1, I need 70%. And guess what? I can develop that further. I can have it 1 up, 3 down, and I need almost 80%. So what does that mean? If I'm at threshold, I get 80% correct. That's just a different definition of threshold, isn't it? There is no such thing as the threshold. There is just a way of measuring it. And 80% threshold is an interesting one because you almost always get it right. You get it in 4 out of 5, you get it right, but you're still at threshold, according to this definition. What does it mean? That there's actually, for the subjects, this is very satisfying because they more often hear the sound than they don't hear it. Because what's frustrating is that the experiment that I did with you, where you didn't know where the sound is. So you don't want to operate too often in that area where you have to really guess. You want to give them something to work with, and you want to push this level up so that they more often know where the sound is. But they have to get it 3 times right. Sorry, 3 times right. Then you go down. 1 time wrong, you go up. And you can combine that now with the either 2 AFC or the 3 AFC. So this is a complete table of everything that is in psychophysics has ever been done effectively. What you don't want is a 1 up, 1 down pure tone audiometry. This is pure tone audiometry. Good question. That's your question for Friday to find out. It takes much longer. That's the short answer. That's right.
When you talk about the variability, you do that with pure physics audiometry, but also when you were saying choose A or B.
Yeah.
So if they get it wrong, you go back over and play the A or B again.
Yeah.
So play 2.
Yeah, you always play 2. You never play 1. You always play 2. So your question is not did you hear it or did you not hear it. Your question is always was it in that one or in that one? Was it in A or in B?
And then you do that again.
Yeah.
At that same.
Yeah. Again and again and again.
And if they get it wrong both times, you move up again.
If you get it wrong, every time they get it wrong, you go up 1. That's not on here. So you get it wrong, you get it wrong, you get it wrong.
If they got it right the first time.
Yeah. Doesn't matter.
Then you go up.
That's the case here actually. They got it right the first time, but they got it wrong the second time. It just matters if they got it right twice or they got it wrong once. Yeah, yeah. The short of it, it just takes too long, but you could still do it if you wanted, especially since you could automate it. And there is a lot of tradition involved in here, so and paradigms of what kind of apparatus you have at your disposal in order to do an experiment. You also want a kind of human interaction. You want to look them into the eye, which is an advantage if you're talking to people, but it's a disadvantage if you think about it psychologically, because you press the button, you know that you're playing a button. You say, yes, you hear it. It's not good. You want it criterion free, you want it blind. Ideally you want it double blind so that the experimenter doesn't know if there is a sound either. Which if you automate that obviously is always the case. But in PTA, haven't got that. Is there a rule? I don't actually know. There is a rule that you shouldn't give it away, don't you? So you're not actually looking at the participant when you're doing it, because that would be skewing it.
Even in PTA, for anything, one sound, if say you have a permutation, you do already have hearing loss, and like you said, you skip through the steps.
Yeah.
Hold it for you. We're only playing 1/10 for the move.
Yeah.
It's not an A and B choice. Could you not send permutations to 1 up, 2 down, but just with
Yeah.
pressing the button?
Yeah,
That
you
would
do.
be more
In fact, PTA is a kind of a modified 2 up, 1 down, isn't it? Because it actually say, and I should know that, I should know it by heart, but I don't. The PTA procedure says you need to get it, you get it right twice before you go down, isn't it? You tell me. you get 2 out of 3. 2 out of 3. Okay, it's kind of a modification of that, but you do not trust the equilibrium. The guessing, the one up, one down. It's not like that. It's a little bit different.
You don't play it. So say I got one roll and then one side, and then go round. What do I do about that? You don't play that same one right after it. No, but you're going to play it with all the best. Would it be better if you then, so I've got one roll, I whack up my side, I get it right.
Yeah.
Would it not be better if you then double check that same level again before you start going back down?
Probably, potentially, but yeah, but you do exactly the same thing again, so it's not necessarily that you expect a different answer, so you don't necessarily learn very much again from it. But what everybody does it slightly different, and that's why everybody gets slightly different results and different thresholds, don't you? The long or the short of that, and I shouldn't say that on record, but I do here, is that audiologists don't really care about that very much. Why? Because we're not measuring thresholds that precisely anyway. What are we doing here? We're measuring a 5 dB. 5 dB is quite a lot. Certainly not around the J&D. What was the J&D? The just noticeable difference? We discussed it in the tutorials. Remember? What did I say? 2 or 3 dB, yes. We did 5 dB, which is easily hearable or audible. And even then, if you take 10 audiologists in a room and do 10 PTAs, I bet you that you get 10 different results of that. And why is it not a problem? Because what you actually give to the hearing aids, there's a number of steps. So you measure with an error. You put it onto the hearing aid with an error. You put it into the ear, there is an error. Because I don't know if you do the real ear measurements, but the real ear measurements might have an error of 5 dB easily, maybe more. So everything that we do is imperfect and imprecise. So why bother measuring it on a dB? Here we can measure it on a dB precision, but the result would be not useful to actually fit the hearing aid. That's why we're not doing it. That's a longer answer. Because we could have an exact answer. Your hearing loss is 27.3 dB. So what? You don't really care. If the answer 30 dB plus minus is good enough to actually put a hearing aid on somewhere. Okay? But take-home message, thresholds are very difficult. No, they're not difficult, sorry, but they're very subjective. And we need to have a good definition of the threshold, and we need to understand that. Hearing loss of 20 decibel means a completely different thing depending on the person, depending on the experimenter, depending on the method. Because it means a different thing if I use a 2 up, 1 down, or a 3 up, 1 down. Gives you, if I say 20 dB threshold, is a different thing altogether. Because here they would get 80% correct, here they only would get 70% correct. But it is fine as long as we know what we're doing. We can do whatever we want. We need to describe that. Here's the message for your research project next year. You can do whatever you want, as long as you describe it exactly and you motivate it. You can come up with your own criteria, your own method to measure thresholds, but it needs to be motivated and explained. That's what science lives of. That's why there are so many different versions and not just one version that everybody uses. Okay, and that is a natural time to do a break. And because the next